Welcome to Chapter 17, where we begin our series of multiple regression lessons. So this is the first one, so today's going to feel a little introductory. So we're going to take the idea of simple linear regression and compound upon it. If you have not watched the Chapter 14 and Chapter 15 video, you should go back and do that now. So what we're going to be looking at is the multiple linear regression model, which you can see below. It is the last equation. And above it, the first equation you will see on this slide is the simple linear simple linear regression model, because it uses just one variable. So I'm hoping you notice that before that we were like, oh, B0, that's the constant, and then, B1 times X. Why did we choose B1? Well, because when you hit the multiple model, you might have lots and lots and lots of variables, and each of them will have their own coefficient or their own slope. So when you hit the multiple model, you'll have x1 and x2 and x3, or any number of them depending on how many predictors you might need. Okay, so the following data was taken from Zillow.com, and this is home price versus number of bedrooms in just one specific city, Saratoga Springs, New York. Because if you did this for lots of cities, well, it would be, a little impossible. Anyway, so if you take the data for price and separate it by number of bedrooms, you can make the following box plots. And what's interesting about this is I first state, hey, this is approximately linear. So you might be looking at this and thinking, how are we getting approximately linear off of that? If you take the medians of each box plot and connect them with a much straighter line than what okay, that was just terrible. We're going to erase that. Sorry about that. If you take the data and connect it with a relatively straight line through the medians, you notice, well, it's a relatively straight line. So on average, it looks pretty linear. That's how I'm saying approximately linear. Next up, I say the equal spread condition is super violated. Okay, I'm hoping you remember that how you judge spread for box plots is the width of the IQR, which is the width of the middle 50% or the width of the box on the graph. And it starts out tiny and gets bigger and bigger and bigger. Clearly, this violates equal spread because none of my IQRs are even close to each other. There are a couple of them that are relatively similar, but the second you throw in a third one, they look different. So we're going to be a little cautious with this data for that reason. So here is the simple linear regression model for this. And you look at it and you're like, okay, so intercept, pretty small, so that's a house with no bedrooms, which, kind of makes sense, maybe not really at all. It's like a studio house, weirdly, with the openest floor plan ever. And then every bedroom I add increases my price by about $48,000. So I'm looking at the coefficients here and evaluating those to see if they're reasonable. And then I look at my my spread of my residuals, and it's huge, so I'm a little unhappy with that. It's about $68,000. That seems a little large for what I'm trying to do. I would like that to be smaller. I'd like it to be somewhere in the thousands, maybe in the maybe like around the 10,000 range would be way better than 68,000. And then lastly, you look at R squared and you're like, well, that's just terrible. That's not a good model at all. Clearly, this isn't enough. And you might be thinking to yourself, well, yes, number of bedrooms is important, but there are other factors when buying a house that we've investigated that clearly impact the model. So maybe we should just include another one to improve the likelihood that I've predicted this well. So we're going to add in living area as a predictor for this regression model. So notice that this changes quite a few things. I'm hoping you look first at the coefficients, because that's what I usually look at first. I'm looking at these guys. And I noticed that, hey, now my intercept is $30,000. So, it changed, but not a huge amount. My number of bedrooms has now gone down, and it's now a negative slope. And then my living area is $93 per living area. So this is probably in square feet is my guess. So for every foot of the house is larger than the previous house, you add about $93, as long as your number of bedrooms stays the same or doesn't change a whole lot. So this is like the additional change you get beyond the number of bedrooms. The other thing you should notice is, oh my gosh, the model is much, much better. Look at that R squared value. It has gotten significantly larger. Woohoo! All right, now we're at 58%, which is kind of meh, but at least we're in the range of not completely ridiculous. Okay, so what does the multiple regression model look like? Well, some things definitely have changed. We're still doing the same thing for residuals. We take the predicted value minus the actual value from it, or sorry, it from the actual value and come up with the residuals. The degrees of freedom is going to be different here. You're using the number of observations you had, aka the amount of data I had. So for me, that was that 1,057 houses minus the number of predictors. So since I was using 2 for this model, it's going to be a little bit smaller. So what's interesting about this is it reduces as you increase your number of predictors. So it becomes less free as you increase predictors. So it kind of makes sense because the degrees of freedom becomes more, restricted or subdued the more predictors you're using. You're also introducing more means. Remember, degrees of freedom is supposed to account for the amount of variation you're seeing in your data a little bit. And every time you include a new variable, you include a new mean that's being subtracted from everybody else. And since it's already in there, it's like I'm reducing what's going on. Okay. Other than that, this formula is identical to the ones you've seen previously. The standard deviation of residuals, aka S, just in case you forgot. Remember, Minitab calls this sucker S, not SE. And just keep that in mind. Alrighty. Okay, so what do we do next? Well, each predictor gets in the regression output, it's just a coefficient, but a standard error, a t-ratio, and a corresponding p-value. This is all the stuff we've seen before. The t-ratio behaves like a z-score, so remember 0, far from 0 is going to be a bad thing, like it always has been, and p-value when we want to be close to 0 because we want it to be small, because we want things to be significant. Yep. So think of t-ratio as like a z-score, because that's exactly how it's behaving. Okay, so in red down below, I've outlined something that's kind of important. Hey, it's a little terrifying that bedrooms is negative. Shouldn't, adding bedrooms increase the value of your home? Be careful. This is something I warned about in the intro. Each coefficient takes into account the other predictors that are present in the model, and you have to be a little careful here. If you're really confused by this, let's do a little bit of investigation. So what I'm saying is concerning is that when we looked at the single variable model, the coefficient on bedrooms, the number of bedrooms was positive, but the second we added in a second variable, it became negative. So it changed so much that it claims, what we really claimed is that the association between price and bedrooms has changed now that this other guy is showing up. And in some ways that makes a little bit of sense because, a lot of your living area in your home will be taken up by the bedrooms that are present. So, this seems reasonable, but at the same time, it's a little bit like, what's going on? Let's take a look at this. So what I've got below, sorry, is so I sort of restricted the living area to around 2,500 to 3,000 square foot homes and looked at just 3, 4, and 5 bedroom homes. So as you look at this, I'm hoping you notice that, oh, well, the slope for this looks, if I just connect my medians, looks negative. That line's terrible. You know what I mean. So as you look at this, you're like, oh, well, why is it negative? Well, think about restricting the living area, but then increasing the number of bedrooms. So same living area, but more bedrooms. Your bedrooms get smaller. If you are trying to sell a home with a bedroom that's the size of a closet, no one is going to want to buy it. So the idea is that increasing, number of bedrooms without increasing living area decreases the value of the home for that reason. So these variables are interacting and acting together with each other to cause this. So the reason why it changed to be negative is because, well, if my, number of my square feet isn't changing, but my number of bedrooms is changing, this is going to cause my house to be worth a little bit less than it was previously. Oh my God, I literally just said all of this. Great. So do more bedrooms increase or decrease the price of the home? Well, it tends to increase them, but only if it also means you also have a bigger house. But it'll decrease it if that means you have smaller, more cramped rooms. So be careful. They're interacting together with each other, not just alone. So be careful with multiple regression coefficients. You really need to interpret them together and thinking about how they're going to interact with each other. And be careful, this is not a causal relationship. We're not looking at necessarily the relationship together, but how they interact with that variable we're trying to make our predictions about, the response variable. So for us, that was price. Let's look at an example. I'll warn you right now, this is not my favorite example. Why? Because I'm not really huge on Broadway. But then again, I really should insult it because I've never been on Broadway. I'm sure they do fantastic shows. Anyway, so in a typical night in New York City, about 25,000 people attend a Broadway show, and the average price of a ticket is about $75 or more. The data for most weeks of 2006 through 2008 consider the following variables: paid attendance in thousands, so the number of people that paid to attend, not free tickets, the number of shows, average ticket price, and then we're looking to predict receipts, so how much they made profit on, which that's not always going to be the same for every single show. Anyway, so the following regression model was produced. So up here we have receipts as our dependent variable. We've got our regression sum of squares and a bunch of information. And notice I don't have the coefficient information on here yet, but that might be what you're interested in looking at. So it is on the next slide. Woohoo! So I want you to look at the following coefficients. So we've got paid attendance, number of shows, average ticket price. What we want to do is we want to write a regression model for these variables and then interpret the meaning of the paid attendance, and then we're going to come up with an estimate for the paid attendance when there were 200,000 customers attending 30 shows with an average ticket price of $70. And then we're going to ask, is this a good prediction? Did it do a good job? And then why or why not? So to build the model, the first thing we're going to look at is the coefficients, and it's as simple as we pull out the intercept and then we do variable times coefficient plus variable times coefficient plus variable times coefficient. And when you do that, you get the following. Woohoo! Oh no, I missed a hat. I was fixing all these the other day and I missed one. Okay, well, the little boxy do is supposed to be a hat. So receipts is going to be negative 18.32. There's your intercept, plus 0.076 times paid attendance. So that's the coefficient for paid attendance times paid attendance. Paid attendance is the position of the variable paid attendance, and so on and so forth. So you just keep adding your coefficient times the variable as you go through and do this. So it looks like a line, but with like some extra slopey doos on it. So interpretation for the coefficient of paid attendance is we want to think about it as, well, the number of shows and ticket price when they're accounted for, increasing by 1,000 customers will give you an average increase of about $67,000. So there's a couple things going on here. If you remember, paid attendance was a decimal. It was its slope was 0.076. So what I've done is I've just taken and done 1,000 of these instead. So if you multiply this by 1,000, you get 76, but remember our receipts are in thousands of dollars, so that's where I'm getting $76,000 from. I wrote 100 and said 1,000. Good job, teacher. Okay, so what we want to do next is we want to estimate what the customers are going to get when the paid attendance was for 20,000 customers, 200,000 customers, I keep saying that wrong, 30 shows, an average ticket price of $70. So we would take each of these and plug them into the previous formula, so 200,000 for paid attendance, 30 for number of shows, and then an average ticket price of $70. You'd take all of those into account and add them all together, and you'd get like 13.89 million. Woo! Okay. Then you ask yourself, is this a reasonably good prediction? Well, our R-squared is 99.9%, so it seems like it's doing most of what you need, right? I mean, I don't know about you, but whenever I see something so close to perfect, I immediately get hugely suspicious for lots of different reasons. And just leave that boiling in the back of your brain for a little bit, and I'm going to come back to it, because it turns out that R-squared, once you hit the multiple linear regression model, doesn't do the best job. Yikes. We're going to need some other stuff. Okay. All right. So What do you need to do to be able to do multiple linear regression? Well, first we need a linearity assumption, and that's for each of the predictors. So when you encounter a new predictor, you need to check it's got a linear relationship with the variable you're trying to predict, the response variable. So here I've got two graphs, one for number of bedrooms and one for living area versus price. So I'm checking each of my two variables from the home price example. So for instance, the one example we just did, sorry, with tickets and attendance, it had three variables in it, so I would have had to do three graphs to check for linearity. And these look pretty linear as far as I'm concerned. I mean, there's some outliers and some spread issues, but it's pretty linear in shape, minus spread. But remember, it's okay to have some spread. You should have some variation. They all look pretty linear. You should also be checking the residual plots for linearity. So after you've created your model, we still have some other things to check inside the residuals. Remember, we want to have the equal spread condition and linearity, but really linearity is the one you need to check for both of these. So here, notice we're doing predicted values versus residuals because you have multiple variables creating your predicted values. The only way you can really check residuals is for all of them together, not them individually. So this is the one from home prices, and it meets the condition because it looks fairly linear. I mean, if I was to draw a straight line down this sucker, it looks pretty good. I'm a little worried about these two, but they're still on pattern, so they're okay. If they were more up a little bit or a little bit more down, I might call them an outlier. This guy is a little concerning as well, but we're just checking for shape here, not outliers. Okay. The next thing you need is the randomization condition. Remember, we don't want biased samples. We want well-collected data. And the only way to really make sure that that is done and we have a representative sample according to our population is to make sure that everything we encounter and gather our samples from is done as randomly as possible to prevent that. Okay. Next up, we have the equal variance assumption, which we can only check by looking at residuals as well. We want to look for relatively equal spread. The big thing with equal spread is you shouldn't see any patterns other than possibly linear. There's no gathering and then spreading, no narrowing and then widening, no fan shapes, no wobbly woos, no other shape other than possibly a straight line. So, and this is how we have assessed equal spread in the past. This is not a new idea. All right, the nearly normal condition. Yay! You want to check to see if your residuals look relatively normal. So we're looking for the characteristics of the normal distribution. The three characteristics we look for are bell shape, unimodal, and is it symmetric? And if you look at the left graph, the histogram, for a minute I just couldn't remember the name of that, it looks like it's pretty symmetric. It looks unimodal. It's got two of the characteristics. That's pretty good. But additionally, you should always look at the what's called the QQ plot or the normal plot. So remember, the one thing you want about a normal plot is you want it to be, I'm trying to draw the straight line in here. When Minitab produces these, it gives you the straight lines. You want this to be close to a straight line. We looked at one of these last week. But as you can see, I've got some curling on the tails and I've got some non-normal tails, and that's definitely being caused by these long little outlier guys looking right here. The non-normal tails are a little concerning, but we only need this to be nearly normal, not perfectly normal. So it's missing some things. It's got some issues, but it's probably okay. So what do you need to check? A lot of stuff. Oof, there's a lot to do here. And don't get scrimpy on your checking. You should definitely check all of your conditions as you go forth and prosper your way into the multiple linear regression region of the world. You should check linearity of each of your scatter plots for each and every predictor, even if that means you got to go through 20 of them. This is one of the reasons why Minitab, when it gives you the scatter plot menu, gives you lots of X's and Y's you can interact with. If linearity condition is satisfied, then a multiple linear regression model is necessary for the data. After you've done this, you should check your residuals and predicted values for near normality, and then inspect the scatter plot of the residuals and predicted values to check for patterns as well as equal spread. Remember, linear is okay, but anything other than that is definitely not okay. Next, you could think about, oh, how was the data collected? Was it independent? Does it look like it was random? Are the data representative of the population if the population in mind was known? Think about the 5 W's and the H from when you first encountered data and statistics. Can I say where it came from, what it's about, when it was taken, how it was selected? That's more of the random component. And where it was taken from. Remember, you can't use things from different areas to try to explain each other. And then, is autocorrelation an issue? Is there an individual in there that's been measured more than once and is used more than once? You know, or an individual that was sampled more than once. All right. Then other condition checks. So if everything in the condition checks, you probably should interpret the model to see if it's useful and if it seems like you have reasonable predictions there to be able to use. So check your slopes like I was doing for the models that we had. Check the values of R squared, kind of. And the value of S to see if you've done a decent job at modeling this. And you should always check your nearly normal condition by looking at the normality plot, or normal plot as I called it on here. And if you have the sample size that's pretty large, remember you got to watch out for skewedness and outliers at the same time. But most of the time when you have something really outlying, we can just throw it out and it'll be okay. But be careful with that unless it's absolutely should be present. Let's look at how to test the model. So there are lots of hypothesis tests you could do for this, but if you're going to test the entire model, you should be looking at the following hypothesis tests. The assumption for our null hypothesis is that everybody's 0. None of this matters, which is a little crazy. All of my slopes are 0. Why'd I even bother? My model isn't interesting. So if you're thinking back to chapter 15, this was a single slope we were testing, and it was a single t we were testing. So instead of doing a single t, we're actually going to be doing multiple t's and a sum of a t, which is actually what's called an F test. You should be thinking back to when we dealt with the chi-square distribution and dealing with the doing chi-square tests. We couldn't do just a t-test because we had more than one proportion we were dealing with there and more than one group with these proportions. Same thing is happening here. I have more than one variable I need to test, and they each get their own t. How am I going to handle this? Well, we need something that does multiple values like the chi did, and that's actually a new distribution called the F. Okay. And then as you look at the alternative hypothesis here, it's like at least one of them is, you know, not 0. And this is the natural opposite of the null. The null is none of these matter, and then the alternative is at least one of them is significant. Be careful with this. This is just testing to see if you at least have something in there that's useful. It's not the same as saying all of them are useful. You can go through and do them individually to see if they are useful. Okay, so be careful. The F distribution has some weird degrees of freedom thingies in it. K is your number of predictors, so its degrees of freedom is n minus k minus 1. And the other thing to be warned about F is that it's a one-sided test. It's always a right-sided test, just like chi. So if you're trying to picture this, it looks like this. And it's a ratio, so it actually starts out at 1. And then depending on its degrees of freedom, this lump is either bigger or smaller, and then it has this really long tail off to the side. And then what you'll do is you'll figure out your F value, and then you will shade, and your p-value will be things greater than this. This is a one-sided test, and it's always a right-tailed test. Always, 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 because it is a sum. I just misspelled tail. Oh my embarrassment. I'm trying to write with... Hopefully you get the idea. Always right-tailed. So we always are gathering our F statistic and then looking at things larger than it. It's an unusual distribution, but it's a lot like the chi. It's accumulating error. Alrighty. So, well, if you get a rejection on the F test, you might ask yourself, which of my coefficients are significant? And then you can do a t-test for each individual coefficient. So be thinking back to like the example we did with the Broadway shows. We had 3 different variables we were looking at. If you end up rejecting that, like, at least one of these is significant, you might ask yourself, well, which one is significant and how can I tell? Are all of them significant, or is it just one or two of them? And the only way you could find amongst those three is to do individual t-tests next. So the idea is we start off with, let's test the whole thing and see if it's good, and then we break it down to see which one of them is going to be the best one. There can be only one, or there might not be any of them that are useful. So from there, we build a confidence interval for the slope, should we want it, for each individual variable. So like there's a bunch of BJs on here. Remember, it's like any of the slopes that we could look at individually. Don't mix and match variables and use different slopes with different variables. That's just bad practice. In general, we don't combine unlike things. Your apples cannot be added to your oranges, so don't mix and match, even though sometimes it's fun. Okay, so I'm avoiding the standard errors completely because they are super hard to compute. If you'd like to look up a formula on how to do them, feel free. They're gross. Minitab will produce them for you every time. They were the column right next to the coefficient columns. They are pretty easy to get off of there. We won't do these by hand. And the meaning for these really depends on what the other predictors are doing, just like how we saw with the prices of homes, the number of bedrooms interacting with the square footage or, size of the house. It was square footage. Area, living area. Totally we're interacting with each other, and that makes these very difficult to interpret. Anyway. Keep in mind if we fail to reject any of the slopes based on the t-test, that does not mean that there is no really linear relationship with y. It could mean that the contributions that it's making is not enough to make a change in how much of y has been accounted for. So it's kind of like if you look at the model and it increases your r squared value by like 0.03. It's not enough of a change for it to be a significant change in what we're seeing in the model. It doesn't account for any additional variation enough for it to matter or be there. And it could be like, think back to living area and the bedrooms. They interacted with each other. They account for each other. They appear to be overlapping with each other. It could be that the variation that variable is trying to explain was already accounted for by the other variable. So when you're looking at multiple linear regression, if each of your slopes appears to be an associated part of your predictor, so as you look at this, like all my slopes are significant, but it looks like they can't all be different from 0, and there's no simple linear relationship between just the two of them, it's possible that, your multiple linear regression is just overfitting. And it's really weird because, like, especially if we see something like the sign change that we got when a new variable entered in, that's highly suggestible that these two are interacting with each other. So if you added a new variable and you notice a significant change in the signage of the previous one you were using, that's highly questionable. All right, back to our ticket prices example. So I sort of ignored this like lower bit of output earlier on purpose because I really wasn't ready for us to encounter that yet. But we should really talk about the F value and the P value associated with it. Whew. So as you look at this, oh my gosh, there's my F ratio. Yay! It's huge. One of the things that's important about F is the farther it is from 1, the more significant evidence you have that your model is doing a good job. And as you look at this, that F is huge. It's huge. It's huge. I said that too many times. And our p-value is really tiny. So you look at this and you're like, oh, well, this is statistically significant. I've done a significant job at modeling the receipts present for New York City Broadway shows. The other thing that you should look at is, well, yeah, my R squared is great. So clearly I'm doing a good job here too. But if you're doing the hypothesis test, you really should be looking at the F ratio and the p-value to make this decision. I'm now going to go through and like do this whole thing again because I just realized I skipped ahead of myself. So be prepared. The next slide shall be boring. Hey, here's your null and alternative hypotheses for that test. Since there were 3 variables present, ticket price, number of shows, and average ticket price. Did I do ticket price twice just now? No, I forgot attendance. Ah, gosh. Sorry, I'm now yelling at this. I'm hoping you're not listening to this on headphones full volume. Don't do that. You'll destroy your hearing, and then you'll be like me, kind of deaf a little, just a little. Anyway, so I've got my three variables right here making my null hypothesis, and then my alternative is, hey, one of these guys, or could be any of them, or a combination of two or three of them, is insignificant to my model. Hey, and then we go through and we notice that our F is ginormous. Clearly this model's doing something. They are definitely not all zero. At least one of them has to be doing something, because like, look at that F, yo. It's pretty, it's significant. Okay, p-value super small, reject null. Hey, at least one of these guys is doing the job of predicting enough variation to be able to say something about how Y is behaving. All right, but then you got to ask yourself, well, which guy is doing this job? Which of these variables is helping me out here? Which of them is telling me what's going on with my tickets? You know, who's predicting my receipts the best? Well, we're actually not going to look at the best, because occasionally statistics is super depressing. Lots of death happened earlier when we were talking about insurance, and now we encounter that, oh my gosh, which of these is the one that is different? That was the worst thing ever. Hey, one of these things is not like the other. There's the words I was looking for. So I look down the p-value column first when I'm doing this, and I immediately notice that, hey, look at this guy. My highlighter's doing a bad job. That's a fairly big p-value. Uh-oh. One of these things is not like the other, and it appears to be number of shows. So, uh-oh. Paid attention to average ticket price were both significant because their p-values were super tiny. However, number of shows is not significant. Its p-value is definitely bigger than 5%, because usually that's the cutoff we use, and probably should be removed from the model because, well, honestly, it appears to be doing nothing, which means it doesn't mean that it's insignificant completely. It might be the fact that whatever it was adding was already accounted for. So we really should be removing it from the model and going down to just two predictors. And this is something that's really important when it comes to judging whether or not your model is good. We want to have the fewest number of predictors possible because we don't want to overfit. So good means that everything is significant as possible, and we don't overfit, and we don't have too many variables floating around. And that's a hard thing to accomplish. And now for something completely different and a little bit confusing. Oh boy. There are lots of ways that you could measure the variation present in R. In a multiple linear regression model. Blurg. Here are just some of them. Some of these should look familiar. So the first thing we look at is the error, or the residual error, among just the values that are present. And then we can look at the regression sum of squares, which is a little bit like the residual errors, but it's how different you are from the mean. It accounts for how much you vary from average in the model. And then there's the total sum of squares, which is how different all of the data is from average in the model. So when looking at our total sum of squares, it's the sum of the residuals plus the sum of squares. Creepy, right? Here's how R squared is normally done. It's your sum of residual error divided by total error. So it's looking at how far you off, how error divided by total to give it relative size. We can also think of this as the difference in residual error from the total. Now, really what R squared is trying to do is measure the fraction of variability that's accounted for by the model, but there's a little bit of a problem with this. For every new variable you add, it inflates R. What do we mean by that? Well, as you look at your degrees of freedom, where is it? You got coming up down here, this is K. Remember, K is your number of variables or predictors that you're using. For every K you add, that numerator equation gets a little bit smaller, and the denominator guy gets a little bit littler. So really, when we're looking at these two, yeah, it matters how many you're using. Additionally, we're going to be careful here because, well, since R squared is in the calculation of the F ratio, if R is 0, F is also 0. So yes, looking at F to decide whether or not your model is significant is absolutely appropriate. But again, R has some problems. If you have large K, this looks like crazy pants town, because your numerator will be super huge, and your denominator, you're subtracting by something that keeps getting bigger. Yeah, down here. And so you're getting a smaller denominator, larger numerator. This starts to blow up really quickly. That's a bit of a problem. So how do we solve that problem? We use what's called R-squared adjusted. R-squared adjusted sort of imposes this weird, I call it a penalty in these notes. It imposes a penalty on correlation strength for all the models. Basically, it says, hey, if you're going to use lots of predictors, well, then you're probably overfitting. The problem is that for every single variable you add, R will always increase. Always. It always gets bigger. And therefore, R squared always gets bigger and never decreases. So even if what you're adding is insignificant, it gets bigger. So is it really good at judging the model, even if you're adding something insignificant? Heck no. That's crazy pants town. So when we're judging whether or not our model is doing a good job, we're going to be using R squared adjusted. So although R squared is still going to tell us about the fraction of variability that is accounted for, we're going to use R squared adjusted when it comes to judging whether or not our model does a good job. Once we've decided that judgment, we're going to move to use R squared to describe what we know about the model and how much it explains. So what's interesting about this is now we're on the level playing field of, okay, I have lots of variables, lots of different combinations I could use to create a model. And when I'm trying to judge which of those combinations is the best, I'm going to use R squared adjusted to decide that. And then I'm going to use R squared to describe what's happening with that model. So they're both going to be working into helping you what's going on here. And now for the logistic. I like the logistic. It's pretty interesting. It's great if you're trying to model dichotomous responses, which I have literally right there. I feel like I'm reading this a little. What do I mean by dichotomous? Di stands for two, weirdly enough. I know you're thinking bicycle for two, but bicycle built for two. Yes or no, A, B, up, down, all that stuff. The logistic is also used for population modeling, which you will understand as soon as you see its graph in like 3-4 slides. And this is like the on and off switch kind of for your computer. So like be thinking 0 for on, 1 for off. If you've ever wondered what the power button on your computer stood for, now you know. Thanks, binary. Basically, the idea is if I want to re-express something that has a dichotomous part to it, like 1 or 0, you can use the logistic model. We will not be using the logistic model that much. I'm covering this just in case you see it in your future. Let's do an example. So here's your data. Hey, I'm trying to predict spending, and I've got a yes or no response that I'm trying to use. Clearly, this is doing a terrible job if you try to do a linear regression on it. So the blue line is if you try to linearly regress this. Holy crap, that's terrible. I look at this and I immediately think, oh my, we are going to have such a better way to do this in chapter 18 as soon as I talk to you about some different variables that you can use to fix this problem other than the logistic, but this is kind of a fun fix. So clearly linear does terrible. What I want to be able to do is express the lower group along with the upper group, the yes and no grouping, in a better way. So here's the problem. A good linear model really should use as few predictors as possible, but at the same time, like if you only have one predictor, you're going to get something terrible like this. I mean, and if you try to do just a single predictor, like just take the average, you're going to get a single number for the yes and the no groups. So clearly this is not enough. I need something that mixes these well, and the logistic does a decent job at this. Here's what it looks like. I know, right? It's this little s. I'm hoping, long, sort of lazy s, I guess. I'm hoping what you get out of this is, yeah, population modeling makes way more sense for this. You start out with a small population that slowly grows, then once you hit like a decent number of people, you're able to increase your rate of growth really, really well. I'm talking about like this range-ish here, right? You know, where you've got like steep growth. And then, you know, your population starts to die off as you lose resources and it sort of stabilizes. Provided you believe that it will stabilize and not just go colonize another planet. I'm talking about people, obviously. Anyway, so this is what the logistic model looks like. It includes the probability of success within it. It's a little bit interesting. Minitab will produce a logistic model for you because the real thing you want to do here is predict the probability of success here. And so you need to take this equation and solve for P. If you don't remember algebra, pause for a minute, ask yourself how to undo a logarithm. It's called an exponential. So you'll have to exponentiate both sides and then rearrange a little bit, add, subtract, divide by some stuff, and then you get the following. That's totally what you were guessing, right? The logistics super weird. There's other logistics too that account for population size and some other things as well. But this is a useful one if you have a yes or no response and you want a continuous growth from one to the other. To give you an example of a place where this gets used is if you have a population that changes a little bit each year and you want to have a smooth transition from one year to the next, the logistic model can be used to do that. There are other things that do this as well though. So what do you need to be able to use this? Well, you need independence and randomization, but you no longer need linearity and equal spread, which is one advantage to this model. Fun facts. All right, that's all I have for you. I'm going to go over the review now. So those of you who don't like to watch me go over the, hey, what could go wrong and what did we learn thing, this is where you leave me. I will miss you. Reminder, the logistic you do not need to know. I will not be assessing you on it. It's kind of a fun fact I'm including for literally no reason other than, hey, it's kind of cool. Hope you liked it. Sorry if you didn't. I feel depressed now. Okay, what can go wrong? Be careful about the hold constant thing. This is the #1 mistake I see students make and other individual statisticians make when describing multiple linear regression. They'll say, provided that all of my other variables remain constant, this is what the slope means. Yeah, don't do that. That's never going to happen. There's no way you're going to get everything else to stay the same and be able to get a realistic response. And really, that's something that only works if what you're looking at does not change with time. And so it's not all that often that happens. Anyway, don't imply correlation is causation. Yeah, I brought it up again. It's like the 5th or 6th time. Don't do it. It's bad. Be alert for a combination of predictors that may take you outside these range of these predictors. This is the idea of don't extrapolate unless you know for sure that you're okay. Even then, if you're going to extrapolate, keep in mind that your model actually might do a terrible job. Be careful when you're interpreting the signs of coefficients. Just because it changes from negative to positive, you should be really cautious of that. I'm sorry, I'm losing my voice a little. Especially when adding variables in and out of the model. If you've got something insignificant, don't waste your time on it. Don't try to interpret it. Don't try to do linear regression on things that aren't linear. Don't do lines on not lines. Doesn't make sense. Anyway. Watch out for changing invariants or residuals. Like when I say this, watch out for SE and or the standard errors of the slopes. Watch for these to change. And I watch S closely when I'm changing my model. I watch S and R squared. And when we hit the chapter 18, I watch my Mallow's cup for all of these. And be careful. The other thing is, always check to make sure that your errors are nearly normal. This is one that people like to skip. You shouldn't do that. If you don't have this, you absolutely should not be using linear regression. And I mentioned high points or influence or outliers, but I'm actually going to do this a little bit more detailed in 18 because we'll have better tools at how to dealing with it. So if you're wondering what the heck is she talking about, hey, that's coming. It's be patient. Patience is a virtue. 18 is a little shorter, so I'm throwing it in there. Sorry. Okay. So what do we know? Hey, I'm going to use technology to make multiple linear regression. And, I should be careful with interpreting each of my coefficients for the models and making sure that each of my x's has an appropriate linear relationship with y and not nonlinear. Whee! I should make sure I check my assumptions and conditions. Linearity is super important. Independence is super important. Equal variance is super important. I already said that one. Oh, crap. This one's important. Hey, check it. So is normality. Remember, we only need nearly normal. It doesn't have to be perfect. It just has to have some of the characteristics of the normal distribution. Hey, when you're checking your linear regression hypotheses, remember, the status quo is that it's a no. It's not something significant. We want to show that it is. So we want stuff that's got small probability. We want to have large F values. We want to have large T ratios. Let's get it big and let's get it significant. Oh, and watch out for your degrees of freedom. All right, what have we learned? Hey, when I'm trying to describe which model I should be choosing, I'm going to use R squared adjusted. When it comes to describing what the model means, I'm going to be using R squared. But be aware that R squared will be inflated. Woohoo! The standard error for residuals equation has changed slightly. It now has a lovely K. Be aware of this. The other thing to watch out for is when you're dealing with the F statistic, remember it's a sum of distributions, so it's always increasing, and that it's a right tail, not a normal looking guy. That is the worst graph I've done in a long time. Let's fix that. That was atrocious. Who lets me draw on here? I'm drawing with my finger because my pen broke. Whee! And it's a heavy tail, so as you look at it, you're brand new to this. As you look at it, be careful. Remember, we're always looking right and shading to the right, especially if you end up doing this using probability distribution plots. And that's all I have for you. I hope you enjoyed lucky number 17. Woohoo! And stay tuned for 18, because I'm sure you're wondering at this point, okay, so now you've talked to me about how to evaluate the model. How do I build a good one? Well, that's what 18 is all about, yo. Good times.